We continue with our low structure. Hybridization, molecular geometry, assessment, and properties which relate to such, like molecular polarity, resonance. Yesterday in discussion class, we talked about species which show this geometry. Trigonal bipyramidal. Bipyramidal. Two pyramids glued together. Trigonal because there are three principal angles. 90 degrees, 180 degrees, and if I hold the model this way, 120 degrees. Now, are these angles guaranteed to be of these values? Yes, if all the peripheral atoms are the same. Yes, if the equatorial atoms are the same, like the three white ones, and the axial atoms are the same. But if I were to be able to synthesize this generally trigonal bipyramidal species, with this atom being different from these atoms, with this atom being different from the other two equatorially positioned atoms, then I wouldn't have bond angles which were perfectly 90 and 120 and 180, but they'd be close. How would you expect the values to compare? Well, it would depend on the relative size of these atoms, their electronegativities, and other properties. So unless we specify a particular atom, we can't really answer the question. But if the three white ones are, for example, fluorine atoms, and the orange ones are, for example, iodine atoms, iodine, a lot bigger than fluorine, so we would well expect, based on the much larger size of iodine, that this angle would open up somewhat because of van der Waals repulsion between the very large iodine atoms. The upshot of which is the angles between the fluorine atoms would get smaller. That would also distort somewhat the 180 degree linearity of the top axial atom with the central atom and the bottom axial atom. All depends on what the atoms are. To answer any question like this, you have no choice but to pay attention to the overall atomic composition of the material in question. And just to demonstrate that a trigonal bipyramid is in fact two pyramids. Here's two tetrahedra, which if I glue together at a common face, I get the trigonal bipyramid. No more, no less. Now, if I hold this solid state trigonal bipyramid model before you, where's the central atom? Well, it's right in the dead center of this model. You can't see it. But if you do a little bit of mental geometry, you can recognize something about bond lengths for a trigonal bipyramidal species if it's got identical peripheral atoms. How will never mind the different colors now on the periphery, imagine they're all the same. How will bond length compare for the equatorial atoms, these, I'm holding an equatorial bond right now, versus, versus bond length for central atom to axial atom? Which one is shorter? Equatorial bonds are shorter. You see, the trigonal bipyramid is rather a geometric anomaly. I think Ben pointed this out in his gathering yesterday. If you have 5 atoms, all of which are alike, connected to a central atom in the shape of a trigonal bipyramid, it's impossible for these 5 atoms to each have the same bond length to the central atom and at the same time be equidistant from each other in our imaginary valence shell. It's impossible. You can't do it. That makes this a geometric anomaly. Now, to go further with this is a solid state model of what? An octahedron? What's octa mean? Well, if you take a look at this thing and count, you'll see 1, 2, 3, 4, and if I turn it over, 5, 6, 7, 8 faces, each of which are perfect equilateral triangles. So octa 8, what's hedron mean? Face. 8 faces. They're all perfect part of the equilateral triangles. Again, if all the peripheral atoms are the same. Ball and stick model. Now, the solid state model shows you that there are 1, 2, 3, 4, 5, 6 if you count them up apices for the octahedron. And those are the positions in space taken by the 6 atoms which surround the central atom for a material which is octahedral in shape. Now, this is a much more regular, a much more symmetrical geometric shape than a trigonal bipyramid. You can recognize that by just counting the number of different bond angles. 1, 90 degrees, 2, 180 degrees, and 3, 120 degrees. But for an octahedron, 90 degrees or 180 degrees, that's it. There are no other bond angles. This is a much more symmetric, uniform geometric shape. It's geometrically simpler than the trigonal bipyramid, even though you've got one more peripheral atom. So with that, let's take off on some of the stuff you did yesterday. You may even have engaged in these considerations. These molecules each have an sp3d hybridized central atom. What's that mean? In terms of number of valence sigma pairs in the valence environment in the central atom. 5 of them. And that means if you got 5 peripheral atoms like this stuff, or this stuff, or this stuff, are any of these sigma pairs in the valence shell of the central atom non-bonding? Can any of them be non-bonding? If you got 5 peripheral atoms. Because at each and every bond site, there's one sigma bond always. Well, if I got 5 sigma pairs and I got 5 peripheral atoms, every one of these sigma pairs for the central atom must be bonding. Okay? So with that, if you've not yet done so, I want you to open up Chapter 10 notes to page 1014. For those of you in lab, which is just about all of you, you should have seen this page already. Because what this page will do for you, if you understand the information on this page, is to put all this stuff that we've been talking about, Lewis structures, hybridization and geometry, all together, and have you realize it's really not difficult at all to make hybridization and geometry assessments after you've done what? What's always first and foremost in plane destruction here? What's first? Right? The Lewis structure. That's right. If you write an acceptable Lewis structure, you have won the game, practically speaking. Because from the Lewis structure, you immediately can count central atom sigma pairs. And from the Lewis structure, you immediately know how many peripheral atoms are bonded to the central atom. And once you know the number of sigma pairs in the valence of permanent central atom, you know how it's hybridized, don't you? 2 sp, 3 sp2, 4 sp3, 5 sp3d, and now 6 sp3d2. Because we got 6 sigma pairs, you got to have 6 valence orbitals. And the hybridized version of these valence orbitals is sp3d2. Not just for fun. If you remember, that once we get to period 3 atoms, we have atoms, each of which have d valence orbitals, 3d. They don't have any d valence electrons, but they've got 3d valence orbitals. Period 3. Sodium, magnesium, on down through argon. And after you go past period 3, you're looking at all atoms, each of which have 9 valence orbitals, discounting F. S, P, and D. Okay. So, theoretically, how many covalent bonds can a period 3 atom make, or period 4, or 5, or 6? How many covalent bonds? How many sigma pairs could it have? You got 9 valence orbitals? You make 9 sigma bonds. Now, very rarely do we find numbers of peripheral atoms for a molecule with a single central atom exceeding 6, but there are some. Why is it? Why do we usually not find more than 6 peripheral atoms or groups for a particular central atom? I've told you a story about this before. Now I'll tell you again. How many basketballs can you glue to a BB? To a BB. You don't like babies? We'll go with a pea. A little green pea. How many basketballs can you glue to a green pea? How many? How many? 2! Ha-ha! But it's usually the case, almost always the case, that for the game we're playing, will the central atom likely be larger or smaller than the peripheral atom? Larger. Well, just by being larger, it has a larger bond capacity. So I'll reverse this consideration by asking, how many green peas could you glue to a basketball? A whole lot of them? Okay? So the larger the central atom, the larger its bond capacity. But, depending upon the size of the central atom, relative to the peripheral atoms, we will never have a size differential which is like a basketball and a green pea. We'll have situations which are more like baseballs and softballs. And if you imagine a softball, about like this here, and a baseball, about like this here, and you try to glue baseballs to a softball, you're likely going to find out that you cannot glue more than 6 baseballs to the softball, because the overall surface of the softball and size of the softball is not sufficiently large to allow more than 6 to be glued to it. That's why you'll find that a lot of materials, especially you'll learn a whole lot about this in Chem 2046 when you talk about materials that are made with transition metals as central atoms. This 6 number of peripheral atoms is very commonly observed. Now, back to this. Which of these do you expect to be polar? This? No, because all the peripheral atoms are identical. How about this? Yes. Would it matter if the fluorine atom now the obvious orange one is simulating the fluorine atom. Doesn't matter if the fluorine atom is here or here. No, still polar. Okay. Well, what about PCl3F2? I'm going to put a fluorine atom back and take away fluorine atom. Is it possible for this thing to be polar? Yes. Reactive atom. Move off. That's that bench. Polar? Yes. Sure. Polar? Polar? You have to pay attention to structure. You have no choice. Now, which one is most polar? This is polar. This is polar. 90-degree angle. The other version is with the fluorine atoms both in the equator at 120-degree angle, more or less. Which one is more polar? 90 degrees. Is your horse sense like it's 90 degrees? Now, tough question. Given that fluorine atoms and chlorine atoms are obviously atoms of different size, how many different bond angles? Well, let's start by seeing which bond angle would be the same. Okay? How about this bond angle? Okay? And this bond angle. Are these the same? Yes. Okay? Are you sure? Okay. Now, you see this bond angle? Is there any other bond angle in this stuff which has the same value as this bond angle? No. Is there any other bond angle in this stuff which has the same value as this bond angle? No. Right. How about this bond angle and this bond angle? Same. Now we've counted up a very fair number of different bond angles, haven't we? More of them. What you got to do to play the game. Now, when we get to SF4, you have to make a decision regarding the appropriate position to be taken by the non-bonding pair, didn't you? So the stick, which is connected to no atom, is simulating a non-bonding pair. If I hold a model like this, the non-bonding pair is equatorially oriented. But I can also imagine the non-bonding pair to be axially oriented. From a Coulombic standpoint, where is the best location for the non-bonding pair? Is it here? Or is it here? Now, where does the answer to this question lie? Where does the answer to this question lie? The answer to this question lies in Coulomb's law. Remember Coulomb's law? We write it as a proportionality. F, force of interaction, is proportional to Q1 times Q2 over d squared. D is the distance of separation between the charge sites. And in this case, the charge sites are electron pairs. Specifically, a non-bonding electron pair versus a single bonding electron pair. Which constitutes the greater region of negative charge density? A non-bonding electron pair or a single bonding electron pair? Non-bonding electron pair, right? Because it's stabilized by one nucleus and one nucleus only. But each single bonding pair is stabilized by two nuclei, one of which is the nucleus which is stabilizing the non-bonding pair. So to whatever degree this bonding pair is stabilized, it's got to be a greater degree than this single non-bonding pair is stabilized, because this is stabilized by two nuclei, and this is a single electron pair, except that it's bonding. That means the repulsion effect exerted by the non-bonding pair on the bonding pairs, provided they're single bonding pairs, exceeds the repulsion effect among and between the bonding pairs. That effect is going to cause these bonds, these atoms in the equator to bend down a little bit. It's going to open up these bonds. It's going to constrict these bond angles a little bit. Okay, we've been through stuff like this before. Or, pardon me, you were through stuff like this yesterday. So then, you see that d squared term in this equation? The force of interaction between non-bonding pair, bonding pair, bonding pair, bonding pair depends mainly on the distance of separation between the locations in space of these electron pairs. And if I have the non-bonding pair here, how many 90-degree non-bonding pair, bonding pair interactions do I have? 3 of them. But if I have that non-bonding pair here, I have now reduced the number of 90-degree bonding pair, non-bonding pair interactions to 2. And that's better. Because the interactions that count the most are those which have the non-bonding pair closest to a bonding pair, and that's 90 degrees. So with this, I got 2 90-degree interactions with the non-bonding pair, as we showed a moment ago with the model. Actually, Orion, I got 3 90-degree interactions, and that's not as coulombically favorable as this. So this tells me, for SF4, I have a molecule which looks like this. What does this look like? Does it look like a seesaw? Right? Teeter-totter. Here's the fulcrum. Did you ever play teeter-totter when you were a kid? Oh, you did something besides all this pushing buttons on computer keys and all that stuff. Hope you went outside and played sometime. In fact, I hope you do that now, all the time. The hell with these computer games. I mean, American youth may well grow up to have the strongest thumbs in the world. The rest of the body will wither away to nothing. You know what that? I mean, when I played seesaw, and I was over here, my partner played, I jumped up. Then my partner did it to me, and I said, oh, that's not so much fun. So I didn't do it anymore. Now then, the same consideration, that is Coulomb's law, arises when you go to IBR3. And in going to IBR3, by the same assessment, you count up the number of non-bonding pair, bonding pair repulsion interactions that are at a 90-degree angle with respect to each other, and you realize that the second non-bonding pair also is better situated equatorially. Clearly, I hope it's clear. This would be poor, wouldn't it? Because now I got a 90-degree non-bonding pair repulsion interaction. That's significant. Well, then you might say, and it is not without reason, that let's imagine that the non-bonding pairs are at a 180-degree angle with respect to each other. Because that certainly minimizes the interaction between the non-bonding pairs. But now if you count them up, you get 1, 2, 3, 4, 5, 6 90-degree non-bonding pair, bonding pair repulsion interactions. So given that the repulsion interactions which matter are those which are a 90-degree angle with respect to each other, we will, by default, you can prove this with arithmetic if you want to, but at this stage of the game, if you sit down with a piece of scratch paper and draw pictures, you'll see that the best location for the 2 non-bonding pair sp3d hybridized central atom situation is for each non-bonding pair to be equatorial, because they're at a 120-degree angle with respect to each other, and that's not anything appreciable. It's that 90-degree interaction that counts. The squared term, the square part that matters. Well then, so when I get to this IBR3 thing, and I hold a model like this, and after having recognized that the non-bonding pairs certainly affect geometry, but they're not part of the geometry. What's part of the geometry? The atoms themselves. So what's this thing look like? Looks like a T. So we call it a T shape. Nothing fancy about that. And of course, if you extend this to one more non-bonding pair in the valence and wire in the central atom, you get the simplest possible geometry, don't you? Linear. Now, that's what XEF2 is. Now, let's go ahead.
What does the d squared term have to do with?
That's not d squared, it's d2.
Oh,
That's counting numbers of orbitals, that's all.
okay, never mind.
Okay? Now then, one more question. Since we recognize that period 3 atoms are atoms from higher periods, in addition to s and p valence orbitals, also have p valence orbitals, how many ways is it imaginable to hybridize a period 3 atom? Well, we've already seen sp, the simplest possible hybridization scheme, because it involves a blend of only 2 orbitals, resulting in 2 sp hybrids, which allows a parking place in space for 2 sigma electron pairs. And then sp2, 3 sigma electron pairs, and sp3, 4 sigma electron pairs. And then we got to borrow from D. When we go to 5 sigma electron pairs or higher. The question is, by playing this game, how many different hybrids can I create from an atom that has valence s, p, and d valence orbitals? How many different hybrids can I create? How many valence orbitals are we talking about? 9? S, single orbital sublevel. P, 3 orbital sublevel. D, 5 orbital sublevel. Okay? So I got SP, SP2, SP3, SP3D, SP3D2, SP3D3, SP3D4. Let's grind them all up. SP3D5. These are all possibilities. And then if I invoke SP3D5 hybridization, how many central atom sigma pairs am I looking at? How many? 9! And I grind up 9 orbitals? Bingo. Now I don't believe you'll be asked to consider anything beyond SP3D2, which, for simplest possible case, is shown by a molecule like SF6. Structure, octahedral, perfectly so, with all the peripheral atoms being identical. You can count the dots and write the Lewis structures and all that stuff, and this is what you'll write. Now, just for fun, take a look at this one for a moment. My question is, if this thing exists, XCF5 minus, what kind of central atom hybridization do we get? XE, how many valence electrons? 8. Remember, double gas atom, family 8. 5 times F, how many? 35. And 1 for the charge. Well, if I do these arithmetic correctly, I get 44 total electrons. But we are not considering any radical species, any species which have half-filled valence orbitals. So I'm going to divide this by 2. Give me 22 electron pairs. Okay, so far? How many peripheral atoms? 5. So how many of these electron pairs are used to create the octet environment for the peripheral atoms? You got 5 of them, don't you? And an octet for each peripheral atom? Okay. An octet is 4 electron pairs, isn't it? Well, with 5 times 4, pretty difficult. There's 20 electron pairs used for the octets for all the peripheral atoms taken together. Is this all right? Are you looking at this paper? Look at it. Because the game I'm playing right now comes straight from this pencil. We got 22 electron pairs. Minus 20 for periph atom octets. Will we expect these peripheral atoms to be octets? Yeah, because this has an even number of electrons, right? So, that leaves me with how many electron pairs yet to be accounted for? 2. So what will be the functionality of these 2 remaining electron pairs? They will appear as non-bonding pairs where? It's got to be on the central atom, because these peripheral atoms are limited to octets, right? So here's what I got. Let's see. Bonding, 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 bonding. Bing, bing. Take long when you play the game. And the game is told you on that page. How's this thing hybridized? How many sigma pairs in the valence environment of the central atom? 7. So how many valence orbitals do I have to hybridize? 7. sp3 D3, how about that? It's just a game. Orbitals aren't real. Although I have met some theoretical chemists who seem to think they are. But let's not worry about those at the moment. How about that? That's all there is to it. Once you count central atom sigma pairs, you immediately know correctly hybridization.
So I know that both pairs of both non-bonding pairs of electrons are on the top first.
Well, we don't care where they're at.
Oh.
All I did was write a little structure. Now then, what do you think the geometry is of this thing? Now we're going to deal with your question. This one is just for fun. I'm going to draw a picture of the geometry, or likely geometry, because there are a couple of possibilities. But I'll draw one that's likely and certainly a shape with which you are familiar. I want you to think of a building in Washington, D.C. What's that look like? Pentagon! How about that? Now then, for this thing, you've got one non-bonding pair up here, and one non-bonding pair behind the drawing surface, with all the fluorine atoms being here. Okay. But if you were to play the same game for IF7, you'd get sp3d3 hybridization, and you'd have 7 peripheral atoms. You'd have here, and an F here, and an F behind, and if you connected these with lines, you'd find out that you now had a pentagonal bipyramid. How about that? Remember we looked at the triangle bipyramid? This would be a pentagonal bipyramid. Fun, isn't it? We can even go to A. Talk about square antiprisms, but we're not going to do that. Okay? So then, enough on that. That one was just for fun. But it had a purpose to show you this game is not difficult to play at all. As long as you keep your thoughts organized. And the thought organizer is all given to you on page 1014. Okay? Now then, XCF5 plus. When we go to XCF5 plus, you'll wind up with our octahedron with one non-bonding pair. So, I'll remove a peripheral atom. Do you recognize that for an octahedron, because of its very regular geometry, that all the geometric positions are identical? We're all set. Okay. And this thing is just an object. It can be blown around in space by the wind. Okay? Well then, I forget which one I pulled out. Okay. Now, what kind of shape do I have? If I have a species with an sp3d2 hybridized central atom and 5 peripheral atoms, one non-bonding pair, here's the non-bonding pair. Well, in your mind's eye, imagine drawing a stick from here to here, and a stick from here to here, stick or a straight line from here to here, and then connecting these base positions. If I connect these base positions with straight lines, what do I have the shape of? Square. And this would look like a pyramid, wouldn't it? It's a square pyramid. All right? Now then, let's go to XCF4. Again, sp3d2 hybridization. So when I get to SPF, so when I get to XCF4, now I got 2 non-bonding pairs. Where should it be? Well, if I have my non-bonding pair situated here for XEF5+, and I want to change this to XEF4, which means I've got to take one more fluorine atom away, and have that pair which was previously bonding become a non-bonding pair. Would you want that non-bonding pair here? And have this non-bonding pair at a 90-degree angle with respect to each other? Terrible! So now we can realize that the non-bonding pair should be here. Species shape? Well, look at it. What is it? It's a square! Now it's all in a plane, so sometimes it's called square planar. A square is good enough. Square planar. All right. Now how about XeF2Cl2 and this business of polarity or isomerism? Do you remember again what isomers are? Isomers are materials which have the exactly same chemical composition but different in-space positions of the atoms that are on the periphery for the species. Well, at a glance you can see XeF2Cl2 is geometrically just like XeF4. It's square planar. 2 non-bonding central atom single pairs, 4 bonding central atom single pairs, and generally square planar geometry, or square as you prefer. How about this one? Is this polar? Yeah. Well, what if I am able to synthesize this square planar version of XeF2Cl2? Is this one polar? No. I have no choice but to pay attention to structure and geometry. Now then, how about OXCF4? Well, if you play with OXEF4, you'll find out that again you have an sp3d2 hybridized central atom. All of these things have sp3d2 hybridized central atom. Okay? And what shape? What shape it is? Square pyramid, right? Now we got 5 peripheral atoms and 1 non-bonding pair. Square pyramid. Any possible isomers? Is it possible to be polar? Is it polar? Well, let's go back to these for this polarity bit. Polar? No. Polar? Polar? Maybe, right? If the fluorines are each axial, not polar. Any other orientation of the fluorine atom is polar. Polar? Seesaw shape. Polar?
Yeah.
Absolutely. Polar? T-shape. Absolutely. Polar? Linear. Polar?
Yes.
And now we're at this one. Square pyramid. Where's the oxygen? This time I ask that you consider the white spheres to represent the fluorine atoms and the orange sphere to represent the oxygen atom. I've never seen an oxygen that's orange, but who cares? Polar?
Yes.
Polar? Yes! Has to be. Right? In general, what this amounts to is, when you have one non-bonding pair in the valence carbon central atom, one non-bonding pair, provided the species is not an ion, because ions are monopoles, they're either plus or minus, or the polar material is partially plus and partially minus, depending upon the positions of the atoms and the relative electronegativities of the species. Okay? One non-bonding pair in the valence environment of molecule guarantees polarity. Does 2 guarantee polarity? Does 3 guarantee polarity? No. So we go back to this. Because that's got 3 non-bonding pairs, and it's linear. You always have to get at geometry to assess polarity. You have no choice. Okay? So we looked at 2 isomers for this thing, where the oxygen atom is at the peak of the pyramid, as opposed to being in the base of the pyramid. Okay? Now, how about XCF3 minus? Well, since we've reminded ourselves that this too is an sp3d2 hybridized central atom, then we know we again have 6 sigma pairs in the valence environment of the central atom. But this time, how many non-bonding pairs do I have? Wait a minute. Remember, this is sp3d2. That means 6 sigma pairs. How many peripheral atoms?
3.
So how many non-bonding pairs?
3.
3. It's all right here. It's not difficult. So, the question is, so I have the non-bonding pairs like this. Is there a different way I can imagine these non-bonding pairs to be arranged? Notice how these non-bonding pairs are arranged. 90 degree, 90 degree, 180 degree. Right. How about now? 90 degree, 90 degree, 90 degree. Which arrangement of non-bonding pairs is better? The one I showed you before, didn't it? Because it had a 180 degree non-bonding pair interaction, which is negligible. So this is best. What kind of shape do I have? Have you seen this before? What is it? How about that? And that's the way to play the game. Again, this is all summed up here. If you haven't looked at this yet, you look at it. Now, a brief comment on orbital electronegativity. For the hybridization schemes which we have considered, SP, SP2, SP3, on down SP3D2. For a given atom, which of these hybrid sets, or hybrid orbital types if you prefer, will have the greatest orbital electronegativity? SP, correct. Why? If I'm an electron, and I move into an energy level, and every orbital sublevel is empty, S, P, D, F, right? They're all empty. I'm moving into this sublevel. Where am I going to take up residence? S, as in that orbital I am most stable. How about that? So from an orbital electronegativity standpoint, the atomic orbital, which has the highest orbital electronegativity, is S. But the hybridized orbital, which has the highest orbital electronegativity, is SP, because it's 50% S character, isn't it? As opposed to this, which is 33 to 30% S character. As opposed to SP3, which is 25% S character. And to get to this, I got 20% S character. And if I go, pardon me, SP3B is 20% S character. And when I get to this, it's only about 16% S character. Okay? So I ask this question. This is the Lewis structure and shape illustrated by Undertaker fluid. What's Undertaker fluid? Anybody know? Formaldehyde, yeah. And here's the Lewis structure for a molecule with which I'm sure you're quite familiar. There's now a whole bunch more up in the room. CO2. The Lewis structures each illustrate carbon-oxygen double bond. Are these carbon-oxygen double bonds for these two different molecules of the same strength and length? Or are they different? Well, there's two possibilities. They're either the same or different. And I will tell you they're different. CO double bond, 2 CO double bond. For which molecule do we have the stronger CO double bond interaction? You see the Lewis structures? Tell me how this is hybridized. And I'll write it down. Tell me. How many sigma pairs? 1, 2, 3. The other one's pi. Tell me how this atom is hybridized. Which of these hybrid orbitals stabilize in electron density to the greater extent? SP, isn't it more orbital electronegative? Which accounts for why the CO double bonds in CO2 are considerably stronger than the CO double bond in formaldehyde. How about it? Simple idea, and it's just a takeoff on electronegativity. Nothing more. One last question, since we've got the picture on board. For this thing, how many different bond angles? Which bond angle do you expect to be the larger? The larger bond angle. Is it HCO or HCH? This one or this one? Well, let's finish today's gathering with a vote. Then we'll explain the vote. Or we'll, shall we say, constructively criticize. It's funny how this word criticize, it has a negative connotation. Criticize only means you take a careful, close look at something. Now, these days, the way the politicians are, criticize means say something bad. Terrible. HCH is the larger angle. How many vote that way? HCO is the larger angle. How many vote that way? It looks like we have about a 50-50 split. Now then, how does the size of O as a peripheral atom compare to H? O is bigger. That means the van der Waals radius of O is bigger than that for H. Now, based on electronegativity considerations, we might expect these electron pairs to be closer to oxygen than they are to carbon, which is true. Well, that would maximize repulsion between the H atom electron, the CH electron pair bonds, and then to spread this apart. But there's one more consideration that you have to pay attention to get at this. This is a double bond, isn't it? What kind of repulsion interaction do you have between a double bond and a single bond? versus a single bond and a single bond? Where's the greater repulsion interaction? Double bond, single bond. This is twice the electron density, isn't it? And that's why this angle is the larger for this species. We'll get up from this point next time, and we've not yet done so. You read this stuff in chapter 10 and 11 notes on Lewis structures for hydrocarbons and molecular orbital theory.